to continue our discussion on physical layer and then move on to data link layer in this particular lecture. So as you know, we've talked about the 5-layer protocol stack with application layer at the top and the physical layer at the bottom. So what the physical layer does is when it gets data bits from the higher layer, it converts that into signals. So we can just say from here you have bits coming in and the physical layer is going to spit out signals. And of course when the physical layer gets signals, it will spit out bits again. Right, so physical layer converts bits to signals and signals to bits. Of course, one is at the sender and the other at the receiver. So we said that in wireless systems we use a modulation scheme. So we are given a carrier signal. So the carrier signal depends on the frequency band that we are given. And it's essentially something like this. It's cosine 2 pi f0 t. This is the carrier signal that we have. Okay, and f0 is the frequency assigned to us, okay, by the government to transmit. So Wi-Fi would use a particular open unlicensed band, okay, and we would use a frequency corresponding to that band. Okay, and what do we do with this signal? Well, we modulate it, and usually what we do is we either change the amplitude or we change the phase. And by changing those, we convey bit information to the other end. And of course, it's possible to even vary the frequency, but most modern wireless communication systems, high-speed data communication systems, will not change the frequency as such. Okay. So basically, what we would do is we would just change the amplitude and the phase. Yeah, of course, there are things like FM radio, where you actually change the frequency itself. Okay. So, if you want to learn more and more about this, of course, you have to take a communications course in the electrical engineering department. Okay. So, the whole course would be dedicated to modulation and coding theory and things like that. Okay. So we said to represent these signals, what we are going to do is we use this constellation diagram. And one example is QPSK, quadrature phase shift keying. So we said there are 4 constellation points. This axis we said corresponds to cosine and this one corresponds to sine at that same frequency. And we showed in the last class that cosine and sine are actually orthogonal to each other. And we said to take the dot product, basically you take integral of one signal and you multiply it by the other signal before taking the integral. So t is the time period for these particular signals. So one of the terms that people use for any one of these 4 signals is something called a symbol. So a symbol is a signal that you send out, okay, and the physical layer term for that is symbol. So here we have 4 symbols. And for example, if you have bit 0 0 coming in, you would send out this symbol. If bit 0 1 came from the higher layer, you would send out this particular signal. If 1 0 came, you sent out this one, and 1 1 for this particular signal. Okay. Of course, we could have a different assignments of bits to each of these symbols. Okay, but this is a good one, and we discussed why in the last class. So what we do is, as we get bits 2 by 2, we send out appropriate single signals one after the other. So I'll just maybe call this symbol 0, symbol, or I think we said symbol 0 0, symbol 0 1, symbol 1 1, and symbol 1 0. Okay. Each of these symbols would, if you look at it over the time domain, it would have some particular sinusoidal shape. Okay, I'm just inventing one signal what it will look like, but it would have frequency f0, but just the phase would be different. So here we are not changing the amplitude when we go from one symbol to the other. All of them have the same amplitude, because amplitude is given by the distance of this symbol from the origin. Okay, so all of them have the same distance from the origin, so they have the same amplitude. Okay. So when we go from one symbol to the other, this phase is going to shift. Yeah, so let's say that this is S00, and maybe S11 might looks something else. Maybe it looks something like this. So what I'm saying is, suppose you have data bits. Suppose my data bits coming from the higher layer were like this. Suppose I had 0 0 1 1 1 0 1 0 and so on. What I would send out as a signal is S00, that is this signal. Then I would send out S11. Then I would send out S10 and then S10. Okay. So for every set of data bits coming in, every 2 bits, I choose one of these 4 symbols to send out, and I send it out. So in the time domain, you would see these things getting concatenated to each other, right? So I would have this signal, then I would have this signal, and then so on. So the receiver needs to know fairly precisely where each symbol starts, so that it can actually try to guess what was sent. Okay, so we said that the signals that are sent out get attenuated, they may face reflections and so on, and also noise gets added. Okay, so it's a very tricky thing to find out what exactly was transmitted. So the signal that we send out, so S of t, let's say, is the signal that I'm sending out, is just a concatenation of these different symbols based on what bits we wanted to send out. And we said that what we receive is, in the simplest case, just an attenuated version of what was sent out plus noise. In a practical situation, you could have multiple components of the signal coming in due to different reflections of objects and so on. Okay, but we'll assume that there's just a single component which is attenuated a little bit. Okay. So in that simple case, we said even then it's a bit tricky to figure out what was transmitted, because although this symbol was transmitted, what we might end up with, because of noise getting added, is that this symbol gets shifted out somewhere. It may get shifted to here, for example. or if the noise is too much, it might even get shifted over here. Okay, so essentially we don't know exactly what's going to happen because the noise could be large or small, it's unpredictable. But we know the probability distribution of the noise, and we know how likely it is that this particular constellation point gets shifted too far off. Let's say it goes into a different quadrant. We know the probability of that happening because the white noise has a particular distribution. Okay. So how do we do that? Well, if we look at each of these components, okay, so we said that suppose we are focusing on only one of these symbols, right? So we are not looking at the full signal that was transmitted, but we just look at the signal from time 0 to t, where only 2 bits were sent. So then we get one of these symbols plus noise, and of course this might be attenuated. So we said that what we look at is the x and y components of what we received. So the x component is just a times what was transmitted plus the noise, and the y component is a times what was transmitted. Okay, so Sx and Sy are the coordinates in this particular space, okay, plus Ny, and these are Gaussian distributed. So you can calculate the probability of getting a bit error based on this. Okay, so let's just look at it in a little bit more detail. So there is this other constellation point, and we said that here we had bit 0 0 and here let's say 1 0. So if this constellation point gets pushed to this quadrant, from the first to the fourth quadrant, notice that the second bit is not in error. I will assign, even though this was transmitted, this is what was received, the Rx and Ry components are here. So I will say, my best guess is that this constellation point was transmitted. So instead of saying that 0 0 was transmitted, I will say that 1 0 was transmitted at the receiver. Okay. So why are we doing this? Well, because even though this signal was transmitted, after noise got added, it could look very, very different. So let's say it might look like something like this. It might look something like this. So what was transmitted? Was it S00 or was it S01 or what, right? And so what we do is we find these x and y coordinates over here, and if it is in the fourth quadrant, we will say that 1 0 was transmitted. But if this was in the first quadrant, we would say 0 0 was transmitted. So if I make a mistake, maybe the noise was too much and it pushed it over here, I would say instead of 0 0, I would say that 1 0 was transmitted. And luckily this bit was not received in error. Though I got the wrong constellation point, I still guessed this correct. Whereas this one I got in error, this bit was in error. So this is a problem, and it's not possible to get all bits correctly all the time. Sometimes the noise might be large, maybe 1 in 1,000 bits or 1 in a million bits might be wrong. Okay? And we have to be able to deal with that. Somehow we have to be able to either correct for the bits or at least detect that a bit error occurred and maybe retransmit the information. Okay. So I will be giving out some assignments on this so that you understand the concept quite well. So effectively at the physical layer we are converting bits received from the higher layer into signals, and at the other end we do something like this. We try to figure out what was transmitted, and with some small probability we'll get a few bits in N. So there are other modulation schemes too. Actually, let's just mention one of them is called 8PSK. So what is that? What was QPSK? QPSK we had 4 points. All signals had the same amplitude. It's just that the phase shifted by 90 degrees. But why do we have to have only 4 of them? We can have more than 4 of them. And last time we looked at QAM, where QAM we actually changed the amplitude. But even if we keep the phase fixed, why do we need to have 4? So with 8PSK, what we can do is like this. So let's say that let's say I just draw a circle like this. And I can choose more than 4 points. Suppose I start off with 4. But let's say that I also choose some other points. So there are these 4 points, but I choose other points too. Okay. So there are these 8 points which I am choosing. All of them lie on the same circle. Okay. So all of them have the same amplitude, because I said the distance of this constellation point from the origin gives us the amplitude. Okay, and the angle from the x-axis gives us the phase. So remember that this is cosine and this is sine. Okay. Okay. So suppose these are the 8 constellation points, then how do we do detection? So we said that effectively what we are going to do for detection is that if a particular received, suppose this is the signal that was received, noise pushed the signal so that this point was received. What we are going to do is we are going to assign it to the closest constellation point that might have been transmitted, and we are going to guess that that was the point that was sent. So we have to divide this 2-dimensional plane into appropriate regions so that we know what is the closest point. So what is this region going to be like? So here we just went according to quadrant. Clearly any received point in this particular quadrant, this one must be the closest, right? And if the received point was obtained here, then we would say this was transmitted. This one is the closest constellation. So here, how are we going to do it? You can think about it. How would you do it? So let's separate out these 2 points. So clearly we want to draw a line between them, and clearly anything on the left of this is closer to this point than to this one. That's fine. Okay. And we can do the same for all of them, pairs of them, neighboring ones. So I will just continue to do that. So I get these sectors. Now if the received signal lands up in this sector, I would map it to this transmitted constellation. If the received vector or the received signal ends up in this sector, I would map it to that constellation. Okay, so you can have any PSK, you can have 16 PSK, whatever you want, right? You just spread out these points on a circle so that only the phase changes, and you would want to spread them out reasonably far apart so that you don't make too many errors, right? If these points are very close, then obviously it's easier to go from one sector to the other. So here, of course, each sector will be 360 divided by 8, that many degrees, right, would be the angle over here. And if we have even more points, then these sectors are going to get narrower and narrower. So there are some advantages and disadvantages with this or using QAM, right? So QAM, you are actually changing the amplitude. So just to recall, with the QAM 16, we had 4 points in each particular quadrant. And it became very tricky to decide which particular symbol was transmitted. So we said if you get anything within this region, then I'm going to say that this particular constellation was transmitted, this particular constellation point. And of course at the edges it was a bit more tricky because this entire region was mapped to these corner constellation points. Okay. So when are you going to use this versus 16 PSK, you might think, right? And so it really depends on the situation. You would have to look at the bit error rate in both cases. But also we have to look at other things. So the nice thing about PSK is that the amplitude doesn't come into the picture. So we said that your received signal is the transmitted signal multiplied by some attenuation. And attenuation is not going to affect PSK as much as QAM. Okay, so just because here this is transmitted, but what you receive is these set of constellation points which are sort of squeezed together. Okay, so here you would have to know the exact attenuation very well, otherwise you could easily guess the wrong constellation point which was transmitted. Okay, whereas here it may not be as bad. So what I mean to say is something like this: maybe this was transmitted, but what you receive due to the attenuation is these same constellation points get squeezed together, right, because the amplitude decreased by so much. Okay. But even if there was no noise, suppose there was no noise, you would still be able to tell which constellation point was transmitted, right? Because you can just look at the angle and say which one was transmitted. Here, because of the attenuation, these points might get all squeezed together. It might look something like this at the receiver. So suppose I sent out one particular constellation point, let's say this one. You don't know suppose you didn't know this amplitude, how much the amplitude has decreased because of the attenuation, you wouldn't know what was transmitted, because this is quite close to the origin. You might think it was this one that was transmitted rather than this one which was transmitted. Okay, so I need to accurately know how much the attenuation is to be able to guess the constellation point correctly in this case. Whereas here that's not required as much. Okay? But of course the attenuation would affect the bit error rate in this case too, because there could be some noise and so. So that's one of the reasons. And another thing is, by sending out the same amplitude for all of them, it may simplify some of your circuit design. Okay, and so here the amplitude would suddenly it be small, but then suddenly it might increase and so on, which might mean that you have to have more complicated or advanced electronics. Okay, so depending on the situation, you would use one of these modulation schemes. Okay. So we'll come back a little bit to modulation when we talk about medium access schemes, which have some relationship to the modulation. Things like CDMA, which you might have heard of. Okay, so code division multiple access. CDMA was one of the 3G technologies. It was quite popular in 3G, and you would have heard of WCDMA, wideband CDMA. Right, so CDMA I would describe as more of a medium access or link layer technology, but of course sometimes the sort of separation between physical and link layer is not so clear, so some people might think of it as a physical layer technology. Another term you might have come across is OFDM. So OFDM and OFDMA are technologies used a lot in Wi-Fi, and also in, of course, Wi-Fi uses OFDM, but your 4G and even 5G technologies will use something called OFDMA. Okay. So we'll talk about those when we talk about the link layer. Okay, but the basics of physical layer is you are converting bits into signals and signals into bits. Okay, one at the sender and one at the receiver.